morning to all. I am Dr. M. Rekha Devi, Assistant Professor of Physics, V.V. Vanyaparama College for Women, Virudhunagar. Today I am going to explain the most important topic in classical and statistical mechanics. The important topic is Lagrangian dynamics. Before going to talk about the Lagrangian dynamics, we are all see about the three basic important topics. The first one is the generalized coordinates. The second one is the principle of virtual work. Third one is the D Alemberts principle. First one is the generalized coordinates. The generalized coordinates is a set of independent coordinates. These independent coordinates fully describe the motion of a system. That means to describe the state of particles in dynamical system. The generalized coordinates are Q1, Q2, Q3 up to Qn. These generalized coordinates depends on n particles. These n particles having 3n degrees of freedom. These generalized coordinates introducing k coulombic constraints, that is reduces to 3n minus k. N means number of particles and then k means coulombic constraints introducing. Using generalized coordinates, the k coulombic constraints equation introducing in generalized coordinates, the equation becomes Q1, Q2 up to Q3n minus k. So the generalized coordinate equation becomes Ri is equal to Ri of Q1, Q2, Q3 up to t. Ri means position. Motion of n particles, that means n is equal to 3n degrees of freedom. This motion of particles subjected to k. K means coulombic constraints introduced. These coulombic constraints introducing k value in three figures. These are all shown below. The next topic is principle of virtual work. The principle of virtual work states that in equilibrium, the virtual work of the forces applied to a system is zero. That means the virtual displacement of ith particle of a system of n particles is denoted by del Ri. That means the total force of any particle is zero. So Fi is equal to 0. The virtual work of the force Fi on the virtual displacement del Ri will also be 0. The virtual work del W is equal to Fi dot del Ri is equal to 0. Del W is the virtual work. So in this virtual work in terms of n particles, the equation becomes del W is equal to summation over I is equal to 1 to n Fi dot del Ri is equal to 0. This results represents the principle of virtual work, which states that work done is 0 in an arbitrary virtual displacement of a system from a position of equilibrium condition. That force we have to applying the force. The force becomes Fi is equal to Fia plus small fi. Fia means applied force, then small fi means forces of constraint. Constraint force is 0, the Fi becomes Fia. So the principle of virtual work equation becomes summation over I is equal to 1 to n Fia dot del Ri is equal to 0. In this case, the work done is 0 in the case of an arbitrary virtual displacement of a system from a position of equilibrium condition. The work of a force acting on a particle as it moves along a displacement is different for different displacements. The third important topic is D Alemberts principle. For a system of mass of particles, the sum of difference of the force, that is very important, the sum of difference of the force acting on the system and the time derivative of the momenta is 0 when projected onto any virtual displacement. That means the sum of difference of the force acting on the system and the time derivative of the momenta is 0 when projected onto any virtual displacement. So that the D Alemberts principle equation becomes summation over Fi dot Pa dot into del Ri is equal to 0. Pa dot is the momentum, Fi is the force, then del Ri is the virtual displacement. So the equation becomes Fi minus Mi Vi dot minus Mi dot Vi dot del Ri is equal to 0. D Alemberts principle generalizes the principle of virtual work from static to dynamical systems by introducing forces of inertia which, when added to the applied forces in a system, result in dynamical equilibrium. These three important topics are very useful for deriving the Lagrangian equations from D Alemberts principle. I hope this is very useful for us. Thank you.